Welcome to 12th lecture of course on corrosion, environmental degradation and surface engineering. Topic of this lecture is the fracturegraphy. As it has been mentioned, a fracturegraphy over here, question comes, is it something new which we are going to learn? To some extent I say no, it is not a new, we have learned a number of times kind of a fractographs, and one of the fractograph has been given in this case, which has been covered in the earlier course, earlier lecture also. We showed earlier there that the cleavage over here, in this case you can see the division, and we also showed the dimples. So, this topic has been to some extent covered in our earlier lectures also, but we want to make much more meaningful results or maybe say much more meaningful outcome from this lecture. So, what we say the fracturegraphy, how do we define it, is a study and analysis both. We want to learn it and do analysis. What kind of analysis is something like what will be the morphology, what will be the traits and what will be the pattern of material which is getting fractured. So, in this case we are talking about only material fractures. So, question comes, we have discussed about the wear, we have discussed about the fatigue and we have discussed about the fracture. Is this fracturegraphy will be only related to fracture? No, it will be also related to fatigue, it will also be related to the wear. So, whatever 11 lectures or maybe 12 or 13 lectures which have been covered earlier, we will have a relation with those lectures in this case. So, what we say again fracturegraphy, we need to study and analyze that material fracture, and how do we define a fracture as such? Generally, common definition is a separation and maybe say disintegration of a solid body into two or more parts as a result of its stress. It can be fatigue stress, it can be tensile stress, it can be bending stress, it can be any stress, but fracture should happen, material should get separated in more than two or maybe two or more than two parts. And in earlier lecture also we discussed something about the fracture. We say the fracture process involves a crack initiation and crack propagation. Again crack initiation, we have discussed that there will be a number of discontinuity in every structure, because most of the structures are the polycrystalline and will have some sort of grain size, grain boundaries, and there will be some sort of indication for crack, maybe say very minute crack, but we really require sufficient energy or mechanism to make it initiation or to initiate the crack which can be propagated. Many small cracks cannot be propagated. So, in this case we are emphasizing crack initiation and finally, the crack propagation too, which will be lead to the failure of this. So, these are the things which are already been covered to some extent. Now, what is the really new thing which we are trying to address in a fracturegraphy? There are many new things which will be addressed in this case. However, I am trying to collect earlier information in this lecture, so that overall good flow of the course happens. So, in this case we are saying under magnification, because most of the time we have given figures which are 10 micron, 5 micron, which cannot be seen with the naked eyes. As an earlier lecture I mentioned that lesser than 50 micron we will not be able to see anything. So, we have presented most of the time SEM images which are magnified, and even if the optical microscope is there, that will give the image which is magnified. So, under magnification we want to really look at what are the fracture initiation sites, what are the propagation paths, what are the secondary cracks leading to the further failure, and what are the different patterns. Like in this case we have shown the dimples, and we also have discussed earlier lecture beach mark, striation or cleavage and many more kind of this kind of patterns. So, in a way I say that fracturegraphy requires a magnification instrument such as optical microscopy, SEM, TEF, that is a transmission electron microscopy, to enable topography and morphology of fracture surfaces. Sometimes we also need a chemical composition of the fracture surface to understand whether there is any oxygen or any chemical reaction or some sort of other phenomena happening along with the wear phenomena. So, we really require those kind of instrumentation for fractography. Now, we have shown something like a dimple in slide. We say the dimple microstructure, which is commonly observed in the metals and alloys which are subjected to fatigue loading, is a kind of a surface pattern of microscopic depression or indentation. Under cyclic loading, the small cracks or flaws whatever we have in the material can form kind of stress concentration sites or stress concentration locations. These cracks will spread if there is a more load on the surface and then finally come as a little dimples on the surface. We also saw some sort of a cleavage fracture. We say the cleavage fracture is observed along the weak planes, whatever the grain sizes on the grain boundaries or the weak sizes or weak sites as such. So, often cleavage line results in a smooth flat fracture surface. We find more like a kind of a knife which are like cutting the butter, something like that. So, that kind of the fracture surface will come, and this cleavage fractures are produced by the process of the fracture propagation. So, there is already crack there, and then this gives follows a path of the weak planes. That is what we say that is involving only the fracture propagation. The presence of the grain boundary and the polycrystalline material can influence the cleavage microstructure. Often cleavage and ridge steps, and another terminology I am using here, the ridge. People use something like cleavage and the ridge are the same or maybe can be compared, but in a real case ridge is a little more complicated compared to the cleavage. It requires a little more energy and there will be some sort of more protrusion of the ridge. I will be showing that in one of the slide. So, I can say the ridges are long, narrow and elevated step. They are bit different cleavage. It requires little more energy for the fracture or the damage in this case. So, let me start with now this lecture with naming something like a multi-mode fracture, because most of the time we find a multi-mode fracture, it is not a single mode fracture, and this is also a SEM image which I was shown in earlier lecture. What we showed there, that the microvoid fracture, we showed intragranular crack fracture, and we showed also the cleavage fracture. So, in one fractured surface we are able to observe the microvoids, we are able to observe the cleavage, we are able to observe the intragranular crack fracture. Now, new thing which in the previous slide I showed some sort of dimple, and here I am using the new terminology microvoids. To some extent it appears to be the same like a dimple and microvoids, but there is a slight difference in this case. Dimple can also occur in kind of the brittle fracture, the part of brittle fracture, but mostly the multivoid fracture occurs in ductile materials. So, that is why we say that the microvoid fracture mostly often is present in ductile materials. I can name the few ductile material, it can be copper, aluminum, steel and maybe many more in this case, and this is a subject of the plastic deformation. We know that when there is some sort of gap or maybe there is some sort of initial the discontinuity in a material, and then a material is subjected to tensile stress, what will happen? Then microvoids will develop inside a structure. So, it is because of the loading, and plastic materials can really bear to some extent plastic deformation. They can change a little bit shape, and that is why the microvoids are generated inside the surface. These microscopic voids grow and increase maybe the numbers by connecting with each other, and finally, it will try to degrade the surface. So, it looks more like a dimple, but in this case we say that it is a completely on a ductile side, while the dimple can involve also some sort of on the brittleness. We say the ductility in a microvoid side will be little more compared to the dimple side. So, there is no as such final division, but from understanding point of view we say that the material is a little more ductile, microvoids will be there, material has a lesser ductility maybe than the dimples will be there. Now, in this sometime dimple on the bigger size, people feel something like a crater which has been shown in this case, but this crater is a really little bigger than the dimple or micro voids at all. And then in this case what we say, it really requires much more energy, it is like a sudden failure. I like impacting, the big ball is impacting the surface and there is a kind of we say that the cavity is created or depression is created or deformation is being created. That is what we call as a crater, and that also been observed a number of times in the fractured surface. So, we want to differentiate, there is a micro void, there is a dimple, there is a crater, maybe the magnitude or size will differ, material properties will differ to some extreme. Now, another one as I mentioned here, cleavage and intergranular in the crack fracture, we say the mostly the cleavage occurs whenever there is a grain boundaries, and then because the grain boundaries are already weak planes, and then if there is some crack already available, it will follow the path of the propagation and then cause a failure. Now, if these are the three failures with the micro void, cleavage and intergranular, I will say this requires a minimum what we say that the micro void will remain if the load is not substantial, very high, while cleavage requires little more load to make the cleavage surface. That means micro void will can bear a more number of cycles, many more number of cycles compared to the cleavage fracture, while coming to the intergranular crack fracture, that can be instantaneous also, and because of that there will be a significantly high load. It is really penetrating the grains itself, it is not looking at only the weak side, but even the strong side are getting damaged because of the very high loads. So, if I write in a load point of view, I say the micro voids will have a minimum to minimum load, even the minimum load will cause some sort of because of the fatigue loading, there will be some sort of micro void. It may not lead to the final failure, but there will be some sort of void formation, kind of a slightly the porosity will be there in the material. But coming to the cleavage fracture, it really requires a load and then kind of weak sides. The weak sides are the kind of grain boundaries, and then there may be some sort of stress concentration, and if there is some sort of micro voids nearby and that is getting connected, then it can really give a stress intensity on the higher side, and that cause a failure. While in the case of the intergranular, we require a larger load, or maybe say more load, much more load compared to the cleavage fracture. So, these are the things which are really required. Now, is another slide I am showing which has been covered in the earlier lecture. What we showed some sort of a hydrogen embrittlement. We say increase of a hydrogen itself will create some sort of a sites, and how that has been shown in hydrogen blistering, and this slide this SEM image has been shown very clearly. There are some sort of a swelling of the material. You can see the swelling here, swelling here, swelling here, and that has happened, reason being the hydrogen embrittlement. Now, if I look at on the fracture surface of a hydrogen embrittled material, what we were able to find out is something like here the many ways of the discontinuities in a surface, and this is a kind of the depression, and this is what we say the hydrogen embrittlement can really give us sites for to increase the crack size in this case. If I try to draw a kind of on the surface, so maybe at some depth, and there is some sort of hydrogen embrittlement here, and maybe some sort of crack is getting generated and is getting connected with this kind of blister. There is a possibility the crack will propagate this side, crack will propagate this side, and maybe this surface will get detached from other surface. So, this is a possible, and even it happens in a number of materials including the titanium, steel, and we need to really think carefully what has happened and why the materials are getting failed, particularly for because of the hydrogen embrittlement, and it happens more common in particularly in marine environment. We need to think from that angle also. Now, we want to continue with a multimode fracture. This slide is again we have brought from earlier lecture. We say that we are combining a brittle fracture as well as a ductile fracture. I have seen a number of articles where people divide, oh, there is a brittle fracture, there is a ductile fracture. In reality, these brittle fracture and ductile fracture, they can come in a combination. We do not have a definite pattern, and quite possible number of sites will be there. Few sites will be indicating brittle fracture and a few sites will be indicating the ductile fracture. Then we need to look at the probability, which has a more probability. The probability of the brittle fracture is on higher side, we quote or we classify that as a brittle fracture, and if the probability is on higher side with the ductile fracture, we say, oh, this is a ductile fracture. So, telling absolutely, oh, this is a 100% brittle fracture, this is a 100% ductile fracture, I find that will be very difficult, because both of the kind of the fracture will occur in most of the surfaces, and then we need to really look at what are the causes and then which will be dominating, and if you are able to really calculate a probability, then that will give better indication. So, again here we are showing here microvoids fracture, which is shown maybe slightly different form, a different slide has been shown out here. Microvoids, you can see that is sprayed completely across the surface. Cleavage is basically on the boundaries of the grains, while intragranular there is a penetrating the grains itself, the cracking in this case. So, what we say that the fracture in this case is may be initiated, not 100%, but may be initiated from a microvoids, because there is a slight discontinuity. It is like a kind of small bubble which has been created on a surface, and it may be because of the inclusions, it may be because of now the grain boundaries already have shown that is a weak plane, and maybe some sort of discontinuity in its structure. Now, what will happen at the lighter load, the lesser load, quite possible microvoids formation will occur, that be more than sufficient, fracture will not occur, failure will not occur. But if there is a load increase in the load and then is crossing the elastic shutdown limit, which was covered in previous lectures also, that if the overall load or overall stress is increasing elastic shutdown limits, then there will be some kind of the plastic deformation, and it will be continuously and reversible also. That plastic deformation will elongate the microvoids, and if it happen, then there will be some sort of stress concentration near those edges, and then there is a possibility also the cleavage fracture occurs, or maybe when there is a possibility that it comes near to the cleavage or maybe the grain boundaries, then the cleavage fracture will occur. So, this is also like a multimode fracture, and in my view most of the failures are multimode fracture, only the probability of one failure will increase compared to other, domination of one kind of failure will be more compared to other. That is what we can think about that. Now, I am just trying to differentiate how the things really work, and then it is very difficult to find out exactly one single mode. That is what I am trying to show here. Now, look at this is a abrasive wear in a stone, we are kind of a cutting, is a kind of cutting action in the cutting edge at a high speed, and then we are able to break the stone into two parts in this case, right. However, we have also seen the ridges. So, if I break the stone in two parts using this kind of cutting saw or maybe the cutting blade, then I will be finding the flat surface is kind of a regular flat surface. While if it is happening erosion on the surface, and then we find a number of ridges happening on this. So, even though overall result is same, parts are getting divided in two parts, so maybe the system is dividing or maybe surface is dividing in two parts, but action will be slightly different. In this case, this is the more dominant in the abrasion site, while in this case the more domination occurs because of the erosion site, more energy is really required and there will be striation. Now, coming to even erosion itself, erosion again will have whether there is a abrasive wear or fatigue wear. So, even this kind of wear mechanism, they are connected with each other. I am just trying to show here that if the angle of impingement, angle of attack is 30 degree, we find some sort of a plowing component in this. So, what is the meaning of plowing? Is something a building of edge or maybe some sort of more deformation or plastic deformation will occur. While in case of when the angle is a 90 degree, this is what we call as a fatigue wear in this case, reason being the pits will be much bigger in the size, that has been shown here. In this case, pit formation will be there, even though area is lesser, but depth will be more. Now, here that the surface is trying to get a sustain more energy in a lesser area. So, the depth of the penetration will be more, damage will be more compared to the area. So, even in the say in abrasion or maybe erosion also, particularly this is a erosion A and B, erosion case when the angle of impingement is 30 degree, cutting action is more dominating, or we say the abrasion is happening more in the dominant manner, even though it is a part of erosion. While coming to the 90 degree, the fatigue wear will be more dominating in this case, or what we call as the impact wear will be more dominating in this case. So, we need to really analyze the product in a manner, and then once we know the debris and what is coming out, what is the really characteristics of debris, we can understand what kind of mechanism is happening. If the debris size is kind of fatigue wear debris, then we can say yeah, there is some possibility of impact wear, or maybe the angle of attack is a 90 degree, or maybe we can see the material also. We know very well the ductile material will not sustain this kind of load, and maybe so the brittle material will not sustain 90 degree, while ductile material will get cut at the lower degree. So, these are the different material, different characteristics. So, if we are able to observe the debris or material composition, we can think about the wear mechanism or the failure mechanism or fracture mechanism. Of course, question again and again will come, how am I really connecting the wear with a fracture? So, maybe in next few slides I will try to cover that. I showed this slide in also one of the previous lecture. We say that this is the disc of a MR brake, and MR means a magnetorheological brake. We try to remove the brake shoe in from this the brake system. We say there is no need of the brake shoe, and then we can really go ahead with this kind of unit, but we observe a multimode failures. What is a multimode failure? You can see here the particle get embedded into surface, and that was a part of the MR particle we thought over. They get embedded in the surface. This is also kind of embedment. While in this case you can see here there is some sort of a crevice is getting made in the surface. Similarly, in this case here. So, this fractograph is really providing a lot of information. So, we can't say the only one kind of failure, and then when we are trying to develop a new system, there will be a number of possibilities, and then overall we understood that this surface needs to be hardened to on a hard side. Reason being, whatever the particles which are coming in a contact, they are little more harder than the disc, and then if there is a particles are already spherical in its shape, they get embedded, and then the 3-body abrasion becomes a 2-body abrasion, which is much more harmful for the system, and we need to change the hardness. So, this is what I am trying to show, that the multimode and then the fracture or maybe the failure of the surface. Now, why I am using the word fracture? Reason being, whatever you can see here, there is some sort of a groove coming out. Naturally, when there is a groove, material has been removed from a surface, and any material which gets removed from a surface is kind of the fracture in my view. So, if material is getting separated from a surface, it is a fracture from that surface. Now, I am trying to show a next 2 slides also, which I have covered in earlier course or the earlier lectures of this course, is something like 2 slide, which is say that how do you identify a fracture? By observing the fracture lines, and then we say that there are 7 different kind of fracture lines, and if we are able to observe those fracture lines, we can say what kind of mechanisms is really playing major role in this case. And then we started then the slide, that time slide, the fracture lines reveal the important detail of the fracture mechanics or mechanisms, and then what will be the crack propagation routes, and some sort of how the material will behave, particularly for the different kind of forces. So, what we have shown, the chevron was a line, it says that if there is an impact, what will happen, this kind of lines will be there, or maybe high energy impact, immediately the cracks will form, and immediately it will get propagated. While we showed the second line, that is something like a beach mark, which is very common in most of the fatigue failures, and you can see here that a lot of plastic deformation, and it takes a number of cycles to develop this kind of surface. So, that was a beach mark related the fracture surface. We in the previous in this when I was presenting this slide, and one of the other earlier lecture also I mentioned that if the plastic limit goes beyond certain limit, the load which is increasing continuously increasing, and the stresses are going along the plastic limits, then there is a possibility of ruptured marks, and this ruptured marks are the very sharp depth in this case, and you can say that we can really look at this like in the gear teeth which are there on a surface. So, this indicates very clearly that load is substantially high. This is a benchmark is a regular fatigue phenomenon, and chevron is something like a high energy impact has happened, and that is why this kind of failure has occurred in the on the surface. So, these three already have been covered. Now, remaining 4, we say the ridge, cleavage, ridge and cleavage I have already compared in previous slides of this lecture. However, we can really see whether whatever we mentioned was clear or right or wrong. We say the ridge marking are lines that represent the elevated ridges, and this has been shown is something like when I show the 2 stones or maybe the 2 parts of the stone, and then because of water they are getting separated, and we are able to find this kind of pattern on the surface. See, something like a material is getting displayed, but it is not getting completely removed, and then they make elevated surfaces on that. While coming to cleavage is something like a knife, we are cutting it, like as I mentioned the butter and the cut from a knife, that surface comes maybe slightly curvature, but mostly the smooth surface will be out, and that is what we call the cleavage mark, and then the ridge mark in this case. And we know the shear lip is something like a ductile fracture, and then there is a lot of plastic deformation on the material and getting separated into surfaces, and that is what we call the shear surface. And this is the most common, we say the multi crack. Most of the time we find this kind of failure. We do not find exclusively cleavage, exclusively the ridge formation, exclusively the shear lip. It is not really happening. Most of the time we find a multi-mode, multi-type of the cracks, multi-paths, and then which path is more dominating, we need to really figure out. Now, if it is a stress coming from because of the corrosion, because of the hydrogen embrittlement, naturally we need to remove that cast. Now, if it is coming very high shear lip or maybe say a kind of the plastic or excessive plastic deformation, naturally we need to think about the load in this case. Now, if there is some sort of brittleness is increasing and fracture is happening because of that kind of a ridge mark or maybe a cleavage mark, naturally we need to think why the brittleness is increasing. Is there any sort of environmental impact, or we need to change the material. So, once we know this kind of lines, we can take a very good decision whether material need to be changed, whether an operating condition need to be changed, whether environment need to be slightly changed. We need to make some sort of closed system where the environment can be controlled, while instead of going for uncontrolled environment. So, this kind of understanding is important whenever we are thinking about kind of a surface engineering or mitigation of the surface failure or surface degradation, or maybe the corrosion degradation. So, this kind of understanding will be important from that point of view. Now, coming to the main part of the lecture, we say fracture versus wear debris, and I believe that many authors they have not covered this kind of topic, and if it is covered to be not to great extent. So, that is why we say that the main focus of the lecture is really fracture or wear debris, or we say that major part maybe the 2 component or 2 subsystems are really causing a fracture, or maybe getting divided in 2 parts or 4 parts or many more parts, will that be case. So, in my view fracture is a really a failure which is a kind of much higher level. Wear debris is also failure, and it mostly will be available in mechanical systems. If I can judge what is really happening in a system by observing wear debris itself, I can get a lot of insight what has gone wrong. Whenever we are trying to innovate, we are trying to do something new, failures will occur. But if I wait till the fracture happens, that is not going to really give me the right solution. If I observing the wear debris at the beginning itself, I can take a number of corrective actions, and overall solution will turn out to be much faster and much more reliable. That is why I am giving emphasis on wear debris, and again I am trying to show that wear debris itself is a part of the fracture, but maybe at a very micro scale or nano scale. Fracture may be a macro scale, we are looking at the micro scale or nano scale. How and why I am just trying to show, or maybe to explain it. We have shown this diagrams. We say there is a stainless steel shaft, there is a carbon graphite mechanical seal. When this seal is used along with the stainless steel shaft, what happens? The carbon graphite layer gets transferred this layer is a black layer is getting transferred on the surface, and this transferred surface is really reducing the coefficient of friction, but it also causes a with a time removal of this layer or delamination of this layer also. So, material is getting transferred, that is the additive mechanism, and then over the running in presence of water, these particles also will get removed slowly and another layer will come. So, what is happening? One is the material is getting transferred and finally it is getting removed from a surface, and fracture is something like if any material is getting detached from a surface, I can name as a kind of fracture. Now, look at this bearing also I have shown earlier that there are number of scratches on this. If there are number of scratches, naturally material has been removed from a surface. If material has been removed from a surface, why can't we say this is a fracture? It is a possibility that material maybe at the nano scale, maybe micro scale that has been removed. I do not have to wait for the level or meter level that fracture should happen, then only I will say, oh, it is a fracture. Yeah, if I am able to observe the micro level or maybe micron level or maybe nano level, I should take care, maybe make the things proper way and maybe improve the system so that this kind of wear can be reduced significantly. So, this is what we call adhesive wear, this was a abrasive wear, right. Now, coming to the fatigue wear, in the case of the fatigue wear, what we realize most of the time, as I mentioned the 70 to 80% time, most of the failure happen on the surface, is the surface fatigue which plays more role compared to the subsurface fatigue. While in this case also we showed that there are some sort of maybe some sort of defect in the material, and that gives some sort of initial site for the crack formation, and then when the bubble size or maybe the crack size is increased, then possibility that cracks will get merged with each other, agglomerate and then make a bigger crack also. And slowly because this is now stress has increased significantly or stress intensity has increased significantly on the site of this kind of crack, it will slowly propagate to the surface and this chunk will come out. Now, this chunk itself can be a micron size. I am not saying that this is a big size, it can be 20 micron, 15 micron also. It is not necessary that it has to be a level, but this is a fracture in my view. And when we say this is a fracture, we should utilize a fracture mechanics approach to analyze how and why this wear debris is coming out. Can we really reduce, can we minimize this kind of a failure? So, this is what we say the formation of it, which we already covered in a fatigue case, that is also kind of the fracture. I also showed in case of the abrasion mechanism what has been shown in the I took this as an example of the bearing, but a sketch was also shown because of the sliding motion between the surface 1 and surface 2, there is a possibility of the micro cracks which are there inside the surface, and then finally they come up in the particle, or maybe say that this hump or this asperities gets disintegrated in number of parts. So, this again is a kind of a fracture. So, this fracture can be utilized for this purpose. Now, if I try to figure out what will be the morphology of these particles, I can judge what kind of a load condition is happening inside the surface, how many particles are coming, what is the chemical composition of this debris, I will get a complete information. So, how many particles, what is the size, what is the particle morphology and what is the chemical composition. These are the more than sufficient to really judge, to understand what is happening into the system itself. I do not have to open a system every time and look at the fracture, oh whether part has divided in 2 parts or maybe the fracture completely or not. So, I do not have to wait for this kind of fracture. We say I do not have to think, oh chain has broken completely. Even if I am getting some sort of a debris here, there is like a one particle, another particle, I can find out something is wrong, maybe the corrosion is more dominating in this case, or maybe the thickness, maybe how many particle per unit times are coming out. If I look at the wear coefficient, I can judge, I can really forecast what will be the life or residual life of this chain itself. Before waiting for the failure of this chain, I can take a number of remedies, and that is what is the aim of this course. How do we mitigate the surface degradation? How do we minimize the surface degradation? So, when we focus on the kind of debris and analysis of debris, we can really achieve our target. So, in this case also I have shown this was a kind of a 2 body abrasion, this is the 3 body abrasion, again the particle is trying to chip up this and then this debris. If I again analyze this debris, I can figure out whether there will be ridges, will be more plastic deformation, will be a brittle fracture in this case. So, I can get a more information from that. So, that is why we say our main aim of this lecture is think the wear debris as a kind of a smaller division, or maybe say micron level division or nano level division of the fracture itself, and we should take precautions, we should analyze, because when we think about SEM, we need to make a sample, and the chip with the wear debris itself is on a smaller size. We can really make an easy sample with that. If there is we need to really look at the kind of grain structure, whatever etching mechanism, that also can be done to this kind of debris. Now, previously I tried to explain about in the previous slide, I tried to explain about other mechanism. I presented also this slide in adhesive wear mechanism. What was in adhesive wear mechanism, I mentioned very clearly, there is a more like a bond formation or molecular attraction in the surface, and because of the molecular attraction between surface, there will be some sort of cold welding, and if there is a cold welding, then naturally and sliding motion, under sliding motion, the material will get transferred, and that was shown in this the picture, that material from the soft surface is transferred to the hard surface, and this is a kind of attachment which has come from with a hard surface, and it has come from a soft surface. So, this is the kind of a material transfer happens, and there is a possibility that this material which is getting transferred from this surface, and there is a possibility of the work hardening of the surface. So, even the second material can get some sort of material transfer. So, both this material can transfer material to each other to some extent, maybe the secondary contact will happen, and then there is a possibility that there is a junction growth happens continuously, more and more material gets transferred on the previously transferred material. So, what we find that this is a lump which is getting bigger and bigger size. As it gets bigger and bigger size, and it has a root, maybe say what is a root which is a weaker, and then it finally get detached from a surface. And under detachment, what will happen? It will get crushed, it can come in a plate form, maybe say that peripheral area will be increased in a bigger way, thickness may be almost negligible. So, that kind of and of course, is the characteristics of adhesive wear also. If we get a plate form debris, we say there is a more chances of adhesive wear. And there is also possibility that it leads to the from adhesive wear to abrasive wear also. Now, I say that this is a phenomena happening in adhesive wear, but particle is coming out from a surface itself. Even though initially it is getting transferred, no net loss, but finally as the size increases, particle will get separated from a surface. Now, whether the one material, the two material or mixture of material, it depends on the condition, but finally it is getting fracture. We say the fracture is already we have defined, the fracture means separation or disintegration of solid body into two or more parts, exactly same thing is happening. So, that is why I want to label this as a fracture phenomena, and maybe say wears and itself is can really work with the fracture phenomena also, but maybe at the micron level or the nano level, and we really require to collect the samples. So, we collect the debris and then really look at the microstructure, morphology, pattern, and maybe chemical composition. Once we have that kind of information, we can really judge what is really happening inside a system. So, it will impart more and more information related to the failure while in advance. Now, I am just trying to show in this slide, and almost all the figures have been shown in previous lectures. So, I am not presenting any new figure as such, but I am trying to represent. Now, look at this wear debris. This is completely irregular, no shape as such, right. It looks like a three-dimensional sum figure. Now, this debris is something like a spherical and the micron level. This is like a kind of the plate or maybe slightly curved plate debris, and then question comes, how do we get this kind of spherical debris as such. So, we can relate here that in a three body aberration, if the particle has come out of the one surface, and then it will be subject to 3 body abrasion. And in one lecture also, earlier lecture I mentioned, the 3 body abrasion is much lesser harmful, reason being the loose particle will revolve more number of times, I mean the larger time, maybe almost 4 times compared to the sliding. So, rolling compared to sliding is more dominant for the third body which is coming out as a particle, and because of this rolling action, quite possible the spherical particles become spherical in this situation. So, another thing which is coming, that this particle which has a lot of corrosion kind of thing or oxide formation. So, we really required some sort of analysis, and we also know that every material will be exposed to the contamination. There will be oxide layer on the top of the metal surface, and then if it comes in the debris formation, we can analyze, we can find out some sort of oxide or contamination or maybe lubricant mixture in this case. So, that will give a good indication. If I get completely virgin surface, a fresh surface, that means something is wrong, so the system is not behaving correctly, it is not getting oxide sufficiently or it is not getting lubricant sufficiently, and we need to work on. So, even the looking at the wear debris, analyzing the wear debris or fractured wear debris will provide a lot of information to us. Now, look at this wear debris which has also been presented in previous lecture. In this case, you can see the wear debris size is almost an mm. We have already presented something, if the wear debris size is more than 100 micron, of course, everything is relative. If the size of the whole system is much smaller, naturally I will say, oh, 10 micron itself is much bigger, but like a thumb rule, if any time the micron size of particle size is more than 100 micron, that means where it is significant, and then material is going to degrade, or maybe the surface is going to degrade much faster space or much more faster speed. So, that is what we call as a severe adhesive wear. As I mentioned, this is a plate stripe, so it will be kind of adhesive wear. Sometimes we use the word spalling, and then this is much bigger than because this is on 10 micron, while this is a 254 micron. So, naturally this size is much bigger, and we say the size also matter, shape also matter, number also matter, chemical composition also matter. So, these 4 characteristics are required for the analyzing the wear debris, and that gives good information to us. Now, however, another thing comes, if the particle sizes are many, the number of particles are many, but particle size is almost negligible, maybe say lesser than 2 micron, lesser than 1 micron, then I will be very happy that quite possible I am going to get this kind of surface which is very good from the mating point of view. It is not really going to damage the opposite surface. In fact, it can really act as having a number of micro grooves which act as like a dustbin. So, this kind of surface will be recommended for the long service life compared to even the flat surface, because flat surface will not have this kind of values, and they do not have this kind of values, naturally they cannot really store this kind of particles. Those needs to be immediately separated from a surface or removed from an interface, while in this case there is a scope, there is a slightly discontinuity. Of course, when somebody can say here these all are acting also as a stress concentration point. Yes, possibility is there, but the way it has been shown, it appears, but mostly it will be kind of a round edge at the bottom. If we do not get a very sharp edges, when the few cycles we start getting a kind of round edges at the surface. It may happen because of the material, because of lubricant, because of some sort of a plastic deformation or increase in stress, then it will also deform the natural manner. So, this is a possible, and then we say all this wear debris we have seen, or all the figures we have seen in previous lecture, I am trying to connect with each other. So, the overall flow of the course happens, and we are able to prove that wear debris can be treated as a fractured surface from a surface itself. Now, this is another interesting thing. We say that 3 body abrasion, and we mentioned that the particle sizes are much smaller, quite possible even the very sharp particle, irregular shape particles are getting rounded. So, I should be happy if the number of particles maybe at any stage are many, but size is almost negligible, I can be very happy from that angle, say this is a good thing. However, I may be unhappy also to some extent. Look at the fretting movement, kind of the phatic failure which we have studied, and we know that phatic wear will cause this kind of surface, or will cause this kind of surface. They are very difficult surfaces, and then it happens like a silent death. That is what I used the word last time also, that there is a silent death kind of thing, and happens mostly for the joints like a nut and bolt joints or riveted joints, something like that. So, when this kind of joints are there, what will happen? There will be some sort of micron level vibration, and that is why we say that phatic wear debris often composed of extremely small particle size, reason being that amplitude of vibration is smaller, much lesser, like 1 micron, 2 micron, and then there will be adhesion mechanism, abrasion mechanism, continuation. A particle will get separated from a surface, and the particle gets separated from a surface, and it will have a lesser oxygen. Then if another particle gets separated, then there will be adhesion mechanism between the particles itself, and then if there is some sort of close loop in this case, obviously because of the joining of two particles, even though initially may be a spherical shape, but because of the deformation, because of the joining, they may get irregular shape, and quite possible this kind of shape may emerge also, because there is a continuous action. We say that extremely small particle ranging in a size from nanometer to micron, because of interaction of a corrosion, because the moisture can really pass through this kind of joints. So, there is a possibility of corrosion the particles even get generated will have a lot of molecular attraction. So, will possibility of adhesion, and then when they join together there will be possibility of the 3 body aberration, because there is a micro sliding motion in this case. So, this interaction may cause some sort of irregular complicated debris, and then that can be also in nanometer to micron size. But in this situation I need to be worrying. Initially I said if I am getting too many small particle I should not worry, but if there is a phatic phenomena I should worry, because there is a possibility the particles are getting leaked, I should get information something is wrong, is there any joint, will there be any possibility of phatic wear. If there is a phatic wear I should stop it or maybe tighten it. That is why many times we say that whenever there is a nut and bolt connection there should be regular maintenance. What is the meaning of regular maintenance? Many times we open the bolt, we oil the bolt, and then again we close and tighten the bolt, so that sufficient torque is there and bolt is not getting untightened. If there is a untightening of the bolts, naturally the vibration level will increase, even the amplitude will increase, the particle size also will increase. So, these things are important to consider when we are thinking about the reliability of system, or a system should operate without any maintenance for the longer time. So, these are the important. We say one side I should be happy with smaller particles, because that is going to give very good finish to the surfaces, but if there are too many small particles, but then there are some sort of joints, then actually I need to think over, if there is a joint and there are many particles, is there any possibility of the phatic wear. Now, this study also, and then this slide also has shown in my earlier lecture, which is the crevice corrosion particularly was shown stainless steel surface, and in this case even the surface is not a fracture, but we are able to see the different patches, and then in different patches we say there is some sort of protection layer over here, and then we did a chemical composition. And what is the chemical composition? With it has iron, it has a chromium, it has a nickel also. So, those things were shown also. So, many times when we do a kind of study of the debris, it can really provide a very good information. And then if there is some sort of a debris, and then which says that the particle size is more than 50 micron, and particularly there is a corrosion chances, we should act immediately, so that corrosion can be halted, can be stopped. Otherwise, there will be a brittle fracture and then whole system will collapse. So, if we get even chips, smaller chips, we should start analyzing those chips. We should look at the chemical composition of that, and then say, okay, this is the situation of the system, whether it is working perfectly, not working perfectly, or we really require some sort of a strategy for that purpose. Now, we have discussed about debris, but now we need to look at what is the correlation. What is the correlation of the surface degradation and debris? If we are able to connect, then it will be phenomenal. if we are able to connect what is the surface degradation and what is what kind of debris are coming, can we really interlink and then say how the shape should come out, or can we really predict well in advance also. So, I am just trying to show three different kind of this is a completely abrasive mechanism. In this case I shown, in this case the micro plowing has been shown, micro cutting and micro fracture or spalling has been shown in this case. What is the meaning of that? In this case you can see here that the various debris are very small. It has been shown over here, kind of thin two dimensional chip, it does not have much thickness. So, in this case the particle size is much smaller in both the direction, in the length as well as in the width direction as well as the thickness direction, all three directions. While in case of the micro cutting, we are able to see a continuous chip formation. This continuous chip formation mostly happens in the cutting cases and machine tools, and then that this indicates something is wrong with the system. And coming to spall, we say that many times the adhesive wear causes this kind of failures. However, finally it has to be fractured from a surface, that is why it has been given the micro fracture, or maybe say action is in such a manner that abrasion is happening finally. So, initially it may be a kind of adhesion or material is getting deposited on one surface, and finally it is coming as a form of the complete small, maybe the complete fractured surface is happening, a major particle is coming out of this one. So, this size is much bigger in other dimension also. So, this is one dimension, if I say this is another dimension, both the dimension is substantial compared to other two debris. So, we say that microplowing in this case is not creating more problem. However, it is creating some sort of edges over here, or a kind of the ridge systems in the material surface, while in this case the material is getting removed, while the material in this case is getting displaced here, while in this case the groove is being cut, right. Even though in this case the material is getting removed from a main groove, but it remain stacked and remain attached to the surface, it is not completely removed from a surface. So, this is here in this case more plastic deformation, in this case a lesser plastic deformation, micro cutting is happening, while in this case a complete fracture is happening from a surface. So, naturally the spall is more like the alarming compared to the cutting or maybe the micro plowing in this case. So, what we say that decohesion is something the removal from a surface of a wear debris, and then it has been shown because of abrasive action is a micro plowing, micro cutting and spalling, and we have picked up this complete figures from a reference which was published in 1981, and then they try to relate that time event surface and debris. That is very important, because in the recent time we have started working on this. Say it is really important. Can we relate surface degradation with a debris which is coming out? Can we connect these two systems? Can we start thinking how to avoid well in advance, even there are debris, and then by analyzing we can really think in this case. So, if I want to express, we say as per my understanding, there is a correlation between the one material surface and feature of the debris produced during the wear process. There is a need to understand how topography, composition and morphology of the one surface affects the characteristics of the wear debris. If we understand it, then it will be have a better picture for us, and we can really think about maintenance in a better form. Under what we have covered something like a micro plowing, we say in case of the micro plowing which is happening because of the abrasive particle, ductile material get displaced to some extent, but not completely material is getting removed. It is basically displacement or maybe plastic deformation, and overall in this case what I understood that wear constant or non-dimensional wear constant which we studied in earlier lectures, it will be lesser than 10⁻⁷. So, it is acceptable in this case. However, coming to the micro cutting action, we know very well the hardness matters a lot in this case, and even asperity contact kind of asperity angle will also matter a lot in this case. In this case, what will happen? that where a non-dimensional wave constant may be lesser than 10⁻³ also. So, it is a 0.001 lesser than 0.001, which is alarming, and we need to think about why micro cutting is happening, and then how do we stop it. So, there is a need to worry about this system. So, I say micropluing will not be worried that much for micro cutting. Yeah, we need to worry about that. Now, coming to the spalling, which was mentioned in this with the 2 dimension, then the particles, the particle has a 2 dimension, and both are significant in this case. Micro cutting only the 1 direction, while in case of the spalling will be 2 direction, and this can happen like a kind of the loose fragment, and mostly it is happening in the kind of a brittle failure. So, again we need to worry what is really happening, why the brittle failure occurs even in ductile material. Is there any kind of weak side, weak plane, and then is there any possibility of the crack. So, need to worry from that point of view. So, we can say that by observing the wear debris, we can judge the effective loading condition or maybe say operating condition, and we can really take a remedial action on that. Now, we will just cover a couple of examples in that. We say that let us think about the correlation between the wear debris and the surface, and that has been shown in this case, and particularly in this case we are using the word dry condition. What is the importance of dry condition? Adhesion will also be there. If I make it the lubricated condition, quite possible adhesion will be removed. So, in this case we want to really look at what is the correlation, how the debris will come out, what is the relation between the surface and the wear debris. And in this case particularly the steel the specimen has been used, and in the steel specimen we say that there are 2 heat treatment process which have been utilized, and then we want to know which heat treatment procedure is going to give better results compared to the other heat treatment procedures. So, we have a 2 heat treatment procedures, and then we want to test which heat treatment will give better results. Again, under this testing we can go ahead with a normal condition, but these tests were conducted under very we said that accelerated condition. The loads were increased significantly, and this detail has been given in 2016 this paper. I am just trying to only summarize what is interest to us, and then how surface and the wear debris are related. You are able to see here there are some sort of grooves here, and then corresponding wear debris which has come out has been shown over here. So, they are trying to establish wear debris and then the micro groove which have been cut on a surface. A similar kind of things also have been shown. Instead of the complete micro groove, we are able to find out some sort of a pit formation over here, and then the wear debris also has been shown in this case. And of course, even the rich kind of the wear debris also has been shown in this case. So, there is a heat treatment 1 and heat treatment 2. The natural question will come which heat treatment is better. And again I use the word, both are operated under dry condition, it is not a lubricated condition. So, which treatment is really better? So, we need to look at it in slightly different manner. We say we need to examine the wears the worn out surface, and we need to really analyze the wear debris, and then we are able to find out in both the cases there is a plastic deformation. So, in absolute sense, even though we have done accelerated test, but load is beyond certain limit, plastic deformation is happening. So, is it really correct? If there is a possibility, we should reduce the load. However, if we have to just compare only the kind of heat treatment procedure, we do not have to really worry about any other mechanism. Then in this situation, say I need to say, yeah, in this case we are able to see the micro cutting, we are able to see micro pulling, because plastic deformation is also visible, micro cutting is also visible, and micro fatigue fracture is also visible, because when you look at the chip there are some sort of marks on that, and all 3 are happening because of abrasion. So, fatigue is also related to abrasion. It is not, these are not connected. Both the cases we are able to find out some sort of scratch marks, we are finding some deep marks also, and we are finding the white grooves also. So, in both the treatment we are able to see those kind of things. However, when we try to figure out debris size is bigger or smaller, so we are able to find out in case of the heat treatment 1, a specimen which has come out of the heat treatment 1 in comparison to the heat treatment 2, where debris which is getting generated in heat treatment 1 case are bigger or longer, and that is why we say the heat treatment is not as good as the heat treatment 2. If I have to just compare 2 only, if I had to compare overall, I say both are bad, and we should think about slightly different kind of heat treatment which can really give the good results, longer life in this case. So, in this case however, because observing this kind of the debris, we say the longest debris specimen which is related to heat treatment 1. So, that is on a worser side compared to heat treatment 2. Now, what is really observable phenomena is that microflowing, microcutting and microfatigue process are occurring in all 3. Even if I reduce a load or increase a load, again this phenomena will be there. The only magnitude will change. Quite possible the load is almost negligible, there is a possibility microcutting occurs, but that possibility may be 0.1% of the, or maybe say the very low 0.05 something like. Microfatigue also will be there, because if we are going for the more number of cycles, then we will be able to see that. So, these are the important thing. In every case, this multi-mode fracture mechanism which was studied or maybe described in the previous slide will happen. Only thing we need to really look at what is overall characteristics, which is more dominating, and find out the results from, or maybe say do a corrective action, mitigation action according to that. Now, let us take another example. And this the example has been taken from another reference which was published in 2010. We say that and what they have done, they use some sort of a reciprocating wear tester to assess the behavior under again a dry condition. Again there is no lubricant, is again a dry condition, and then they kept a sliding distance something like 1 kilometer or 1000 meter, and then they try to compare the results. And we again there are the two surfaces, we in one case they are using the base material, another case they have made a nanostructure material, and then they are trying to compare whether nanostructure material is better compared to the base material or not. However, they have compared from a debris point of view. Now, what is a debris point of view? I say that in this case, as there is a dry condition, in this case both adhesive wear as well as abrasive wear will occur in both the cases. Now, if you look at the base material case, chip sizes are again in much bigger compared to the second case, which is a nanostructure material. However, the chips are getting formed in both the cases, and then when we try to think from a 3-dimensional point of view, and I widely think, oh, maybe debris is getting separated from a surface, can I attach this debris back on the surface and think whether really everything is like getting attached properly or not, and based on that I can really focus what will be the life of this system. So, this is an important concept, and most of the time we call this as a digital twin. Can we rethink the completely constructing the body back from a debris itself? If it is possible, then we will be able to really do better service, better maintenance, and then beginning means we do not have to wait at all for the real failure, but even continuous manner we can improve the service from that machine. Maybe I try to explain in a slightly different manner. Let us take a gear teeth. Now, we know the gear teeth has an involute profile, and if there is some sort of debris separation happening from a gear teeth, even it may be nano level, naturally involute profile is going to get changed to some extent, and there is a possibility the pitting failure will increase and maybe getting populated. So, why shall I go with that kind of a stage? Why not we take remedial actions well in advance? That is what we are trying to think, and that is what we say the digital twin can be utilized. So, let me explain in my way. We say the wear debris, worn out surface and digital twins are 3 maintenance related concepts. I am using the word because the degraded surface is maintenance related concept, where debris is concept related to maintenance, and digital twin, which is a new one recently been started, is also maintenance related concept. Now, where debris have been explained to the detail, and then even the surface which gets roughened and material loss has been detailed, has been explained in detail. And then we say that when we see the surface degradation, then remaining useful life of the component, we can think about the plant maintenance, or maybe we can make some sort of a strategy for the maintenance purpose, and then we can prevent unanticipated failures in this case. So, we need to have a relation between the wear debris and surface degradation. As I mentioned, the digital twin is slightly different, and what is a digital twin? Maybe a number of sites will explain to it, but what I think and what is my way of understanding, I say a digital twin as a digital copy of physical object or system data from wear debris source including sensor, IoT devices or simulation can be combined with a structure or physical system which we are using, and then we can make something like we can construct a deteriorate system. That means if the wear debris is getting removed from a surface like from gear surface, can I remove in a digital copy of the surface and then really make what is a really the closed system happening in the physical system. Can I really make a digital copy on my system and try to figure out what will happen next. So, it is basically kind of people use the word something like a cyber physical system. However, I just wanted I do not want to go to the like a computer intensive services cyber physical system. I say it is really required from maintenance point of view. We will think from a tool as a tool for a maintenance work as such, and then we want to use this tool to track, evaluate and improve the performance. In my view, digital twin can help in making decision when it comes to the maintenance by giving a real time insight into the state of physical asset, like as I say, I use the word gear, maybe the bearing, maybe very costly machines also, and then we can predict the failure wear pattern, and then we can really assist maintenance also. We can plan everything well in advance. So, or maybe we say that we can make a system in a manner it can run for the years and years, and then if there is a fault we can immediately diagnose and we can do a corrective action as such in situ, or maybe say we can plan when the remedial action should be done. So, in other words, wear debris and worn out surface or visible sign of deterioration which we can see, we can do a fracturegraphy and all. Well, and then the virtual mode is a digital, is a kind of virtual mode, and it allows a real time monitoring and analysis of the system in a digital mode. So, that is a very new concept and good concept. I know it is difficult to really rebuild complete structure from a wear debris point of view, but I am sure that research will be enhanced in this area, and soon we will be able to look at and we will be able to find out complete maintenance strategy completely based on the digital twin. So, now let me cover the two more examples. We say now earlier two examples we covered with like in absence of lubricant dry case, while in this case we are going to cover with some sort of lubricant. In this case what has been mentioned is something like a case study has been given the hip simulator, and this paper was published in 1996, and what is kind of a dynamic load or fatigue load. In this case maximum load was applied around 2450 Newton, and then overall comparison was made for the 5 million cycle is completely fatigue, and then we say that they use three different kind of sample. Is a raw sample, other one is that treated sample, other one is the exposed to the radiation. So, three samples were compared, and here the comparison between the two samples has been given, and in this case you can see the debris generation has been shown. Now, in this case in the first case particularly I am able to see more number of debris, but what author says that the debris, these are not debris, I say that the fibrillation is something that they are using the word which may be required to reduce the wear rate, while in case of the radiation we find that there are number of the voids on the surface which are not very good, particularly for the hip simulator in this case. So, that is what they mentioned, that in this case the wear rate will be much higher, and in this case wear rate will be lesser. And then if I cover it, then what they mentioned, they really studied because this is again a statistical. So, they need to really do a more number of experiment. So, what they did, they took a total 18 cups, and then of course, the material has been ultra high molecular weight polyethylene which has been mentioned in this case. So, they made a 6 cups without any treatment of this material, and then in the 6 cups they use something like a ETO, what they use ethylene oxide, and 6 cups they really exposed to the gamma radiation. So, these two treatments were done, and one was untreated. So, they covered us in they did a testing, and then the 6th time they repeated the results, and then they tried to come up with the results. However, to lubricate it they pre-soaked and all the samples in the bovine serum for 6 weeks, so that the sufficient lubricant or bovine serum is soaked by this kind of samples. And then when they compare, they found that the cups which were which were subjected to the gamma radiation, where it was very high, something like 5.3 10⁻⁶ mm cube per Newton meter, while in case of untreated cup it was only 1.68 into 10⁻⁶ mm cube per Newton meter, while the ethylene oxide treated, where weight was minimum, that was something like 1.6 into 10⁻⁶. However, this is not a significantly different compared to untreated one. So, what they say that gamma radiation, which is bad for the human being or in a real case. So, when this material is subjected, whatever the material they were used is something what, as I mentioned, that ultra high molecular weight polyethylene, if it is subjected to the gamma radiation, performance will be very poor. When the wear rate will increase 3 times, and then we need to avoid this kind of material if we want a good results. So, this is what has been mentioned. Again, I mentioned very clearly, even though the wear debris were little more in this case, but they say that the fibrillation is on a higher side, and maybe that is really required in this case, maybe it is really effectively reducing the wear rate. So, overall we need to look at the wear rate. So, we need to think wear debris, number, size, and we also need to look at what will be the wear rate. So, there are more and more dimensions, or maybe more and more parameters related to wear is coming. Now, we will just take one final example. In this in this lecture, we say we are trying to take another example from one of the reference in 1985, what they mentioned about the wear debris generation due to abrasion, and then they compare hard particle versus soft particle, and they use 2 different kind of steels, which is given A and B, and then this is and the image has been shown for the material A, and this has been shown for material B, and then you can see here the 120 grit size has been used, in this case 180 grit size has been used. We know very well, as the grit size increases, and the corrosiveness will reduce, or maybe hardness of the abrasive particle will reduce. So, this the B is subjected to more harder particle, and what they are able to find out kind of a very long kind of micro cut has been shown in this case, while slightly this is a different. So, we can say here D and E, D and E is something like a micro cutting in this case, while coming to the A and F, AF has been shown as like a micro plowing, while C and the B and C, they have shown something like a fragmented, a small, a kind of brittle failure particularly happening, and that is what they interpret. So, if I think slightly different manner, we say that even though the materials are different, and even the abrasives which they have used a different material and the different abrasives, but they found the characteristics more or less similar manner. So, what they wrote something like a similar kind of similar type of the debris obtained in both the cases, whether it is a softer abrasive or harder abrasive, both the cases they have found a similar kind of debris, and then only the number changes, size changes. What they found, the softer abrasive produces fewer micro cutting chips and smaller pieces of the debris compared to the harder abrasives. So, number is really reducing, and then what we say that overall type of the chips are not changing, sizes are different. If you go for the softer abrasives, size is lesser, number is lesser, number of debris are lesser, but the more or less shapes are same. So, we need to really look at in all 4, what is the size, what is the shape, what is the composition also, and then if all 3, then if we are able to find out what will be the wear constant or dimensional wear constant, that will give a really good results to us overall. So, these are the important aspects, and then as I last in this case they say the SPOL, as I mentioned earlier, we generally find a multimode fracture. It is not only ductile fracture or brittle fracture, there will be some brittle fracture, there will be some ductile fracture, which fracture, which phase is going to dominate, which has a more probability, we need to look at from that angle. However, if there is a more domination of the brittle phase fracture, actually we need to look at what are the weak sites, what are the is there the grain size or some sort of inclusions or the polycrystalline structure, what is really the problem, and then we need to address those kind of problems. So, I hope this lecture helps you to understand the fracturegraphy, and I will say that thank you for your attention. Thank you.